Hey everyone, and welcome to today's Explainer. We've got a seriously fascinating chapter of physical geography to unpack today. If you've ever stepped outside on a scorching July afternoon, felt that intense heat hitting your skin, and wondered, how on earth does our planet handle all this cosmic energy day in and day out without burning up? Well, you're in exactly the right place. We're going to dive right in and unlock the secrets of our atmosphere.
It's kind of crazy when you think about it, right? I mean, Earth gets almost all its energy from this massive, roaring star that literally never stops shining. So if we're constantly being bombarded by solar energy, why doesn't the Earth just boil? Why doesn't it keep heating up until it's a completely unlivable wasteland? Well, today we are going to crack the code on this whole cosmic mystery and see exactly how our planet manages extreme solar energy to maintain a perfect, life-sustaining balance. Okay, let's lay out the roadmap for today. We'll be hitting 5 main sections. First, incoming solar radiation. Then we'll balance the books with Earth's heat budget. After that, we'll look at heating the atmosphere, map out global temperature distribution, and finally, wrap things up with temperature inversion.
All right, jumping right into Section 1, incoming solar radiation.
So, the Earth's surface receives most of its energy in short wavelengths, which scientists call insolation. And because our planet is a sphere, these solar rays hit the top of our atmosphere at a slant, meaning we actually intercept a remarkably small fraction of the sun's total energy. How small? Well, on average, the Earth gets about 1.94 calories per square centimeter per minute at the outer edge of the atmosphere. I know, it sounds like a totally tiny number, but believe me, that 1.94 is the energetic heartbeat of our entire world.
What's really wild is that this solar output actually varies a bit throughout the year. On July 4th, Earth is at aphelion, which is its farthest point from the sun, about 152 million kilometers away. But on January 3rd, it reaches perihelion, its closest approach. That means we actually receive slightly more insolation in January than we do in July. Crazy, right? So why aren't we roasting in January? Well, that astronomical effect is basically masked by other huge factors like the layout of our oceans and land masses and the overall circulation of our atmosphere.
And that leads us perfectly into Section 2, Earth's heat budget.
You can think of this budget like a giant accounting ledger in the sky. For the Earth to keep a stable temperature and, not melt into a puddle of magma, every single unit of energy that comes in has to eventually go back out. So imagine 100 units of insolation hitting the top of the atmosphere. Before they even do any heating, 35 of those units are immediately bounced right back to space by clouds, snow, and ice. This reflected amount, that's what we call the Earth's albedo. Of the 65 units left over, 14 get absorbed by the atmosphere, and 51 units finally make it down to be absorbed by the Earth's surface. Okay, so Earth has absorbed its 51 units. To balance the ledger, it has to radiate 51 units back. Here's exactly how that math works out. 17 of those units are radiated directly out to space. The other 34 units get absorbed by the atmosphere. Now remember those 14 units the atmosphere absorbed on the way in. Add those 14 to these 34, and the atmosphere holds a total of 48 units. Finally, the atmosphere radiates its 48 units out to space. So 17 from the Earth directly plus 48 from the atmosphere equals 65. The exact 65 that came in. The books are perfectly balanced, no missing energy.
Moving right along to Section 3, heating the atmosphere.
We've got the numbers down, but how does this heat physically move around? Well, there's a really crucial distinction here. The incoming solar energy is short-wave radiation. Our atmosphere is mostly transparent to that, so it punches right through to the ground. But once the Earth heats up, it becomes a radiator itself, sending energy back up in long-wave form. And here's the kicker. This outgoing long-wave terrestrial radiation really struggles to escape. It gets absorbed by greenhouse gases like carbon dioxide. So surprisingly, our atmosphere is actually heated from below, by the Earth itself.
Once the ground gets nice and warm, it starts interacting with the air touching it. This process is called conduction. When the air directly contacts the hot ground, it heats up slowly, and that heat transfers upward, layer by layer. Conduction is incredibly important, for sure, but it pretty much only heats the very lowest layers of the atmosphere that are physically touching the Earth.
Now, as that bottom layer of air gets heated through conduction, it expands, gets lighter, and rises straight up in currents. Think of it like a vertical elevator for heat. That's convection. It's a super efficient way to move energy around. But this convective transfer is totally confined to the lowest part of our atmosphere, the troposphere.
Finally, we've got advection. This is the horizontal transfer of heat by the wind.
And honestly, horizontal movement is often way more important for our daily weather than vertical movement. For instance, in tropical regions, especially in northern India during the summer, you get these intensely hot local winds called the Lu. Those are a direct result of advection. The wind is literally just sweeping that heat sideways.
Next up, Section 4, Global Temperature Distribution.
To actually see how all this heat is distributed across the globe, we use something called isotherms. These are basically just lines that connect places sharing the exact same temperature. Now in January, you might think these lines would be perfectly straight horizontally across the map, but they absolutely aren't. Because land heats up and cools down way faster than the ocean, the January isotherms actually deviate sharply north over warmer oceans, like the North Atlantic, and they dip way down south over freezing cold continents. Now let's compare that to July. During the summer, equatorial oceans hit incredibly warm temperatures, well above 27 degrees Celsius. Notice how the isotherms here generally run much more parallel to the latitudes than they do in winter. The sun is really putting in the work, and the heating across the huge land masses in the northern hemisphere is intense. I mean, we're talking temperatures climbing above 30 degrees Celsius in the subtropical continental parts of Asia.
And when you subtract the January temperatures from the July temperatures, the results show this extreme continentality in the Eurasian interior. Just look at the massive spike in the data there. The temperature range is more than 60 degrees Celsius between summer and winter. Compare that to regions near the equator, where the range is a remarkably stable 3 degrees. Being close to the moderating influence of the ocean just changes the whole game.
Let's head into our final topic, Section 5, Temperature Inversion.
Okay, so normally we have what's called a normal lapse rate. Basically, the higher up you go, the colder it gets. But an inversion flips this completely upside down. Picture a long, really clear winter night where the air is perfectly still. Without any clouds to trap it, the heat from the day radiates off into space super fast. By early morning, the solid ground is actually colder than the air hovering just above it. This creates a surface inversion, acting almost like a tight lid on the lower atmosphere. It traps smoke, dust particles, and creates those really dense morning fogs we see all the time in winter.
I actually love how the textbook describes this. It says, being heavy and dense, the cold air acts almost like water. Just picture that for a second. Cold air literally draining down the sides of hills and mountains under the pull of gravity. It piles up deep in the valleys, displacing the warmer air and pushing it upward. This whole process is known as air drainage, and surprisingly, it's actually great for agriculture because it protects the plants sitting in the valley from frost damage.
All of this brings us to a really critical final thought. We've seen exactly how our planet meticulously balances its 100-unit heat ledger and how it relies heavily on terrestrial long-wave radiation passing back up through the atmosphere. But knowing that greenhouse gases are the exact things that trap this outgoing long-wave energy, well, we have to ask, how might human interference and adding more of these gases disrupt this incredibly precise cosmic ledger? It's a fragile balance, guys, and understanding the mechanics of this chapter is absolutely the first step in exploring the vital science of our changing climate. Thanks so much for joining me for this explainer, and definitely keep asking questions about the world around you.